Hi, this is Shuo. I'm gonna keep talking my assignment 6, the project part. So the project 1 of the uh, section 3 is we use the linear regression to resolve the section 2.3 and 1, which is the winning lifter in Olympic Games problem. So the basic assumption we have here is according to the physiological argument that the muscle is proportional to the cross-section area. So we have this relationship, and then we assume that the lift ability is proportional to the muscle, and combined with the first and the second assumption, we have this relationship, which is the lift ability is proportional to the cross-section area. And here the lowercase I represents the length of the muscle. And we know that weight is the production of density and volume. So we assume that density is constant. Since we assume that the lifter is geometrically similar, so the muscle percentage of the lifter is constant. So we have this relationship, which is the weight is proportional to the volume, and the weight is proportional to the cube of the length. So then, so here we have the first model from the assumption, which is the liftability is equal to A times weight to 2/3 power. So if we assume that the height of the lifter is constant, then we have the volume is proportional to the cross-section area. So we have the second model, which is the liftability is equal to coefficient times the weight 1 second power. And so now we consider the refinement to the model. We assume that there is a certain amount of body weight is independent of size. So we have this two refinement model according to the first and the two models. So we add intercept to the model as a constant. So I'm gonna fitting these four models by the data, and the data is also divided in two groups. One is female and the other one is male. So before fitting, I create a performance evaluation function. So in this, so the input of this function is A and B, which is the coefficient of the linear model. A is the slope and B is the intercept. So the first we calculate the residue by the function, and then we calculate the SSE, and then is the SST, then SSR, and the final one is the coefficient of determination R square. And then I'm also going to plot the residue plotting for analysis. So for the female group, here is the data of the female group. And first, I'm going to transfer the data as the first and the second model. And then for the first model, I used NumPy linear regression least square function to calculate the coefficient A, which is 15, and then call the model evaluation function we created before. So we have the performance of the model. We got the value of SSE, SST, SSR, and R square. And also we got the residue, and we also have the residue plotting for the first model. So next we do the same thing to the second model, and we got the result, and repeat the same process to the third model, which is the refinement model for the first model, and then is the last one is the refinement model for the second model. So, and then I'm going to compare these four models. So here is the four models we created. So here is the result is shown in this table. So for the female group, all the models look reasonable. There is no linear trait shown in the residual plot. We can see from the residual plot all the points is randomly distributed. And then the refinement model improved the previous model with the increase of the coefficient of determination, which is the R square, and the value of the residue is smaller in the refinement model. So we could say refinement model has a better fitting for the given data. So then we go to the male group. So here is the data of the male, and first we transform the data to the model we're going to create, and then we do the same thing as the as what we did in the female group. So the first model is the liftability equal to A times W 2/3 power. So we got the result and the residual plotting for the first model. And then for the second model, we got the plotting and results. And here is the refinement model of the first model. So here is the refinement of the second model. So from this is what we built for the male group. So for the male group, sorry, this should be male. So for the male group, the relationship of liftability is proportional to weight to the 2/3 power looks reasonable. So we could say the first and the third does not look good because the R square value is very small. So so we could say the relationship that liftability is proportional to the weight to the 1/2 power is kind of reasonable. And that goes to the next project, which is the heart rate of birds. So what we know is that the blood flow is the production of cross area and velocity. So we have the velocity is equal to the blood flow rate, divided by the cross section area. So we assume the birds are geometrically similar. So we have the weight of the birds is proportional to the cross area. And then we assume the blood flow is constant. Then we have the relationship that the velocity is proportional to 1 divided by the cross-section area. So, and therefore we can derive the relationship that the weight is proportional to the velocity minus 1 power. So I'm going to fit the model by the given data. So here we transform the x value to x minus 1 power. So here, then I'm going to use the NumPy linear regression least square function to solve the coefficient of the A. So we got the coefficient. Then we're going to evaluate this model by the residue plot. So we see that, so this is the residue plot for our basic model. And we can see that the basic model gives us a relative low SSR, and which means it can be used for the prediction in current range given in the data. So, but we saw there are two points is far away from the other points. So we assume that there is refinement model is needed for the basic model. So, and then I create a refinement model and then calculated the coefficient of the refinement model and make the plotting of the refinement model. So here is the result. The model 1 is our basic model, and the model 2 is the refinement model. So here is the comparison of the basic model and the refinement model. As I mentioned before, the basic model gives us a lower SSR, so we can only use this to predict the weight in current data range. So the refinement model gives us a higher R square, which means the refinement model gives a better fit for the regression line. So the residual plot of the first model shows that there is extreme large value. Which means the basic model needs refinement, and the second residual plot looks reasonable because the residual plot, the residues are randomly distributed, and there is no linear trait, no extreme large residue. So the final result shows that the linear regression may not be the best model for this given data set. So let's go to the next project, which is the heart rate of mammals. So this project is kind of similar to the previous one. We got a new data of the weight and rate of the blood of the mammals. So we are gonna to use the basic model as in previous project. So here I got the results, and so the residual plot shows that there is extremely large residue exists. So a refinement model is needed for this project. So that's what I did for the project. Thanks for watching.